In this session, we shall see about deadlocks. Before we shall see what is the definition of deadlocks, let us see an example. Let us see one simple example where actually there are two children, child 1 and child 2. Child 1 is possessing a drawing book and child 2 is possessing a pencil. Both of these are resources. Drawing book and pencil both are resources, and moreover these two resources are shareable. That is, drawing book can be possessed at any instance of time by only one child, as well as pencil can be held by only one child. So therefore here in this example, child 1 is possessing drawing book and child 2 is possessing pencil. Now child 1, in order to start drawing, so actually child 1 requires a pencil which is possessed by child 2. Child 1 cannot continue. So child 1 has to start drawing over the book until or unless child 1 gets the pencil from child 2. And similarly child 2 cannot continue the drawing. Why? Because the drawing book is possessed by child 1. So this is just a simple example. This is just a real-time scenario where actually both of these children, that is child 1, child 2, they cannot continue with drawing. So why? Because so each of the child, so child 1 is waiting for child 2 and child 2 is waiting for child 1. So both of them, they cannot continue. So this particular situation is nothing but, so it is a deadlock. But in the computer system, in the computer terminology, so let us see how actually the deadlock occurs. So here in this session, so these are the contents which actually we'll be discussing. The first topic is what is a deadlock. So here we'll be seeing what is the definition of deadlock. So again by seeing an example. The next topic is, so what are the necessary conditions for deadlocks. Next we shall see how actually we are going to handle the deadlocks. Here in this deadlock handling mechanisms, so we have several solutions, several handling techniques like deadlock prevention, deadlock avoidance, detection and recovery, and finally deadlock ignorance. These are the various deadlock handling mechanisms we have. And in the case of these necessary conditions, there also will be getting 4 conditions. So anyhow we will be seeing them in detail. So first of all, let us see what is a deadlock. So here when it comes, so as we have seen a simple example where the children are competing for drawing book and pencil. So as we have seen that is a real-time scenario. So now let us see in the computer system. So we'll be having several types of resources. So some of them can be physical resources like printers, memory, CPU. All these are physical resources, as well as we'll be having various logical resources like files, semaphores. So we'll be having various logical resources. And moreover, when actually a deadlock occurs in the system, so for this let us take an example. Let us see a CD drive, so where actually it is a physical resource. So that CD drive, it is having 3 instances. That means we have 3 different types of CD drives: CD drive 1, drive 2 and drive 3. So now there are 3 processes: process 1, process 2 and process 3. So process 1 is holding CD drive 1, process 2 CD drive 2 and process 3 CD drive 3. Now actually each of the process, like process P1, again, so in order to complete its execution it requires one more CD drive, so let it be drive 2, but actually drive 2 is held by another process which is nothing but process 2. Similarly process 2, it requires another CD drive which is actually held by some other process. So in this manner each one of the processes, so they are waiting for another process, where actually that process is also waiting for another CD drive. So this particular situation, this particular scenario is known as a deadlock. So coming to the overall definition of this deadlock, so we can see the definition here. A set of processes is said to be in deadlock state when every process in the set is waiting for an event, so that can be caused only by another waiting process in the set. So each and every process will be waiting for an event to be occurred, so where actually that event can be caused only by another waiting process. So even that process it cannot release. Why? Because it is waiting for another resource. And moreover, so this situation will arise. So this particular scenario is known as a deadlock situation. So here, let us see, so as we have seen, so just now we have seen what are the various resources that we'll be having, like CPU cycles, memory space, IO devices. So there are several resources which can be shared among various processes. So now, let us see what are the types of events that occur. So whenever a process, it has to utilize a resource, the following are the three events in general occur. So what are they are? Request, use and release. So what is request is, so each and every process, so it has to initially, in order to start its execution, it has to request for a resource. As soon as it gets the resource, it has to use that resource. After that usage is completed, it has to release that resource. So these particular events will occur. So whatever the process it may be, in order to complete its execution, these are the set of events that actually occurs. So now, as we have seen in the content, so there are 4 necessary conditions for the deadlocks. What are they are? Mutual exclusion, hold and wait, no preemption, circular wait. So these are the 4 necessary conditions that have to be held simultaneously. So whenever these 4 conditions occur simultaneously in the system, then only we say that so that the deadlock will occur. So what is the first condition? These are very important conditions. So the first condition is mutual exclusion. What is mutual exclusion is, at any instance of time, only one process can use the resource. That means the resource is never shareable. So this is the first and foremost condition. So whenever this condition occurs, so what actually we are saying here is, a resource can be used by only one process. So that resource is not shareable. Next, what is the second condition is, process will be holding resource. At least it has to hold one resource and it has to wait for some other additional resources in order to complete its execution. This is the second condition that has to be satisfied. Next comes the third condition. What is the third condition is, no preemption. What is no preemption is, so once the process starts using the resource, it can that means it can release the resource only when the execution gets completed. That means the resource cannot be forcibly removed from that particular process. That is known as no preemption. As soon as the process completes its execution voluntarily, it can release the resource. So in the middle of the execution, so that process, it cannot release. That means another process cannot forcibly release the resource from that process. That is known as no preemption. Then what is circular wait? Circular wait is nothing but, so let us see an example. So here we have some set of processes like P0, P1 till Pn. So let us suppose that there are 4 processes, P0, P1, P2 and P3. So now let us see what is actually a circular wait. So P0 is requesting for a resource which is held by P1. P1 is requesting a resource which is held by P2, and P2 is requesting for a resource which is held by P3, and in turn P3 is requesting a resource which is held by P0. So here we can observe that there is a cycle. That means P0 from P0 to P1, P1 to P2, P2 to P3 and finally from P3 to P0. So we have a cycle here. So therefore this is nothing but circular wait. Each and every process is waiting for some other process. So where actually that process it cannot release. Why? Because it is further waiting for some other resource. So this situation is nothing but circular wait. So these are the 4 conditions that should necessarily occur. So in order to say that, so and moreover the important thing is simultaneously these 4 conditions. So whenever these 4 conditions occur simultaneously in the system, then only we say that there is a chance of occurrence for the deadlock. So they are mutual exclusion, hold and wait, no preemption and circular wait. So now, in order to understand whether there is a chance of deadlock in the system or not, so here we'll be having a graph. So the name of the graph is resource allocation graph. So let us see what is actually this resource allocation graph. So here, and in general we know that graph is nothing but it is a set of vertices and edges. So it consists of vertices and edges. So here we have the vertices is again partitioned into 2 types. So the vertex, it can be either a process or it can be a resource. So in the graph, as we know that we'll be having set of vertices and we'll be having set of edges. So here what we'll be having in this resource allocation graph is, so we can be partitioned into 2 types. So what are they are? Processes as well as resources. So we shall see in detail about the resource allocation graph by seeing an example. So for timing, you try to understand it. So in the graph, we'll be having set of vertices where actually the vertex can be either a process or else a resource. So next comes edges. So the edges are also of two types. What are they are? Request edge and assignment edge. So what is a request edges, and moreover these edges are always directed edges. So what is request edges? So request edge is nothing but a process is requesting for a resource. So in that case the edge will be always from process to resource. Then what is assignment edge? So assignment edge is always from resource to process. What is the meaning of this is, so a resource it is assigned, that means now that particular resource is being assigned to a process. So here in this example we are showing that as from Rj to Pi. What is the meaning of this is the current instance of resource Rj, it has been assigned to process whose name is Pi. So this is the general definition of this resource allocation graph. So let us see with an example. And moreover, so coming to the notation of these processes and resources, so here always the process is represented with a circle and resource is represented with a square. So here you can say something. Here in this particular box we are having 4 dots. What is the meaning of that is, a resource can be having multiple instances. So sometimes the resource can have only one instance, sometimes, so some types of resources may be having 2 instances, some may be having more than 2 instances. So here as we have 4 dots, what is the meaning of this is, this resource is having 4 instances. So next here we have something like Pi request instance of Rj. So in this case we have an edge. So just now we have seen that in the case of a request edge, the edge will be, that means the direction will be always from process to resource. What is the meaning of this is, so now Pi is requesting for an instance of resource which is nothing but Rj. The name of that resource is Rj. So next, coming to this assignment edge, so here what we are having is Pi is holding an instance of Rj. So what is the meaning of this is, the edge will be always from resource to P. So here if you see this, we are having an edge which is pointed towards P. What is the meaning of this is, currently Pi is using the resource Rj. So that is the meaning of this. So here is, we have a complete example. So where actually you can see in this example, so we have 3 processes P1, P2 and P3. We have 3 resources R1, R2 and R3. So as we have just now seen the notation of resource, R1 and R3 are having single instances. So therefore we have only 1 dot. If you see this R2, so we are having 2 dots. So therefore the meaning of this is, we have 2 instances of resource R2. Now, and moreover we have another resource, so where actually resource R4 is having 3 instances. Here if you see, we have an edge from P1 to R1. So what is the meaning of this is, P1 is requesting for resource R1, but resource R1 is already held by process P2. P2 is requesting for resource R3. R3 is already held by process P3. And if we see this resource R2, so we have 2 instances. So one is held by process P1 and another is held by process P2. And finally, so resource R4, so currently no process is using it and no other process is waiting for resource R4. So this is an example where actually we can show the overall structure of a system. So in the system we have 3 processes and we have 4 resources, and clearly we are able to mention so what is the instances of each resource and where actually, that means how actually each and every, whether we have request edge in between the process and resource, or whether we have an assignment edge in between the process and resource. Clearly, so once we show the system by using this resource allocation graph, we can tell whether there is a chance of deadlock or not in the system. So let us see how actually we are able to conclude whether we have a deadlock in the system or not, again by taking another example. So here we have seen, so just now we have seen a simple example. So here we are just extending the same example. Here what is that extension is, P3 is requesting for resource R2. So here what is actually happening is, P1 and P2, so currently we have 2 instances and one is held by process P1 and another is held by process P2. So therefore if any other process requests for the same resource, that process it has to wait. For how long it has to wait is, until process P2 or P1 releases that particular resource. So here we can observe one thing. So here we have a cycle. So that means from P2 to R3. So if we once we represent this, so how actually we are going to represent that is P2 to R3 there is an edge, from R3 to P3 another edge, and again from P3 to R2 there is another edge. So that means, so here we are completely form a cycle. So here once we get a cycle in the system, sometimes, so if the occurrence of the cycle, it may lead to a deadlock, and sometimes even though there is a occurrence of cycle, so there cannot be a deadlock. So here let us see another example, so where actually we can conclude. So here we have a cycle here. So here also there is a chance of cycle. So we are getting that cycle, and that cycle is from P1 to R1, from R1 to P3, from P3 to R2, and finally from R2 to P1. So definitely this is a cycle. So we have a cycle here, but we are saying that there is no deadlock in this case. So how actually we can conclude this is, so if we have a graph and if we don't have any cycle in that graph, so definitely there is no deadlock. And next, the next point is, if the graph, if it contains a cycle, so here if it contains a cycle, so here we get two cases. What are those two cases are? So if there is only one instance per resource type, so then there is definitely a deadlock. That means each and every resource is having only one instance, and the other process is waiting or requesting for the same resource. So actually that resource is already held by some other process. So definitely, so this leads to a deadlock. So why? Because for each and every resource we have only one instance. But if there is a resource, if it has several instances, and if there is a chance of, that means if the cycle is occurring in that particular graph, so then there is a possibility of deadlock. So what it means is, the deadlock may or may not occur. So a cycle is there, and moreover the resources are having multiple instances, but whenever a resource is having multiple instances, even though there is a cycle, we can conclude that the deadlock may or may not occur. So these are the facts that we can draw. So if a graph, if it has no cycle, so just blindly we can say that there is no deadlock. If a graph, if it contains a cycle, so here we need to take two cases. If resource is having, each and every resource is having only one instance, and if there is a cycle, definitely that leads to deadlock. But if the resources are having multiple instances, so there is a chance of deadlock. So finally, so we have methods for handling deadlocks. So what are the solutions? So whenever a deadlock occurs, or how actually we are able to handle these deadlocks is, so we have 4 handling techniques. So the first one is deadlock prevention, second one is deadlock avoidance, third one is deadlock detection and recovery, and finally the last one is deadlock ignorance. So the first one is deadlock prevention. So let us see one by one in detail, and moreover, so just now we have seen this resource allocation graph. We will be using this resource allocation graph. So how actually this resource allocation graph is used is, so in the solutions like deadlock prevention, and in deadlock avoidance, and in this deadlock detection and recovery, so we will be utilizing this resource allocation graph, and finally we will be telling whether a deadlock is there or not in the system. So anyhow, with an example, so we will be discussing them in detail. So first let us see the first solution. So as we have seen, there are 4 methods for handling deadlock: deadlock prevention, deadlock avoidance, deadlock detection and recovery, and the last one is deadlock ignorance. So we will be seeing each and everything in detail in the coming sessions. So first let us see about this deadlock prevention. So what is this deadlock prevention is, so just now we have seen what are the necessary conditions for the occurrence of deadlock. So what are they are: mutual exclusion, no preemption, hold and wait, and finally the last one is circular wait. So when actually we can prevent a deadlock? What is deadlock prevention? So we need to take some precautions such that deadlock will never occur. So here what is deadlock prevention is, we need to take care such that the deadlock will never occur in the system. That means we are taking some precautions. We are taking some precautions such that the deadlock situation will never occur in the system. How actually we are going to take the precautions are, so just now we have seen that the 4 necessary conditions. When actually we can prevent a deadlock is, any one of the conditions should be violated. When any one of these conditions can be violated, so then definitely the deadlock can be prevented. So the first condition is mutual exclusion. We need to prevent this. That means we need to violate this mutual exclusion. So we know that what is a mutual exclusion. Mutual exclusion is at any instance of time only one process can be only one process can use a resource. So what is the meaning of that is, so the resource can never be shared among the resources. So that is nothing but mutual exclusion. Whenever we violate that mutual exclusion condition, what actually we say that is, now the resources can be shareable. That means whenever all the resources are shareable, then we can say that we are able to violate this mutual exclusion. But definitely this mutual exclusion cannot be violated. So why? Because for an example, if we take this printer is always a non-shareable resource. So definitely printer is always a non-shareable resource. So even though multiple people or multiple processes, so they want to take printouts, so whenever they want to take printouts, so they'll be just giving the print option. So all the print options that are given by the persons or by the processes, so they'll be spooled. That means they'll be kept in the queue. But at any instance of time, even though multiple persons they can access, at any instance of time we can take only one printout. That means only one person can take the printout from the person. So therefore definitely this resource is non-shareable. So definitely mutual exclusion cannot be violated. So this is the first condition, and let us see whether we are in a position to violate the other conditions or not. So the second condition that we have to violate is hold and wait. So what is the meaning of this is, so we have just now seen what is hold and wait. Hold and wait is nothing but what? A process will be holding a resource and it will be waiting for another resource. So definitely a process should at least hold one resource and it has to wait for another resource. So then we have seen that this is a necessary condition for the occurrence of deadlock. What we are saying is we need to violate this hold and wait. Let us see how actually we are going to violate this hold and wait. There are two possibilities for this. What is the first possibility is, the first one is, so the process, it should never wait for any resource. What is the meaning of this is, initially as soon as a process starts its execution, it has to acquire all the resources. That means before the process starts its execution, so it has to see that it is holding all the resources and it is never waiting for any other resource. That means here we are breaking that. That means we are not letting the process to wait for another resources. So that means we are just making the process to hold. It is never waiting for another type of resource. But what is the drawback of this is, so here no other process, it cannot tell what type of resources it requires in the life of its execution. So sometimes in the middle of the execution or at the end of the execution, so at the instance of time it may be requiring some other resources. But here as we are saying that it should never wait, initially itself it has to acquire all the resources, so it cannot anticipate the future. So it cannot tell which type of resources it may be requiring in the middle or at the end of its execution. So therefore here we are able to say that this is a little bit difficult to again implement. And another drawback of this is low resource utilization. So what is the meaning of this is, so let us take an example. So now here that process, so it requires both laptop and printer as a resources in order to complete the execution. So suppose that it initially acquires laptop, and even as it requires printer also, even it is going to acquire the printer also. So now here, so that process, it has started the usage of laptop, it has prepared a document, but in order to prepare that document, so it is nearly taking some 20 to 30 minutes of time. But as we are saying that it should never wait for any resource, so initially itself it has acquired the printer also. So here due to this, what is happening is, so until 20 or 30 minutes it cannot use the printer. So as soon as it has completed the preparation of the document, so then only it will be using the printer. So therefore what is actually happening is, so we are going to have less resource utilization. So even though it is able to use that printer after 20 or 30 minutes, initially itself it is acquiring it. So therefore the utilization of resource is very, very less in this particular solution. So even we can break the hold and wait in another type of solution also. What is that solution is, so here whenever the process it has to request for any resource, what it has to do is it should never hold any resource. That means if it requesting for a resource, it has to release the resources which is currently holding by it. That means we have to break that hold condition. So it has to release the resource, then it has to request for some other resource. So in this manner, that means if it wants to request for a printer, so it has to release laptop. So then as soon as both printer and laptop are ready with it, so then only it has to acquire both the resources. So this is nothing but we are breaking that hold condition. It has to acquire the resources. So in order to acquire the resource, first of all it has to release the resources which are currently held by that particular process. This is nothing but breaking that hold condition. So either we have to break that hold condition, or we need to break that wait condition. So in that manner we are able to violate that hold and wait condition. The next one is no preemption. So what is this no preemption is, just now we have seen that no preemption is nothing but, so a process, if it requests for any resource, so forcibly it has to release the resource from another process. So this is nothing but no preemption. So whenever we want to break this condition, whenever we want to violate this condition, so what actually should be done here is, that should be violated. That means the resources can be preempted. That means if any process, if it has no resource, if it has been held by some other process, so this process what it has to do is, it can forcibly take that resource from some other process. So this is nothing but no preemption condition. So in this manner we are going to break this no preemption condition. The final condition. So what is this final condition is circular wait. We need to break this circular wait condition. So what is this circular wait condition is, so we have seen an example with 4 processes. P0 is waiting for P1, P1 is waiting for P2, P2 is waiting for P3, and finally P3 is waiting for P1. We need to break the circular wait condition. How we are going to break this circular wait condition is, we need to impose a total ordering of resource types. What is the meaning of this is, and moreover, so here if you see something like, so each and every process requests for a resource only in an increasing order. What is the meaning of this is, so always P0 can wait for P1, P1 can wait for P2, P2 can wait for P3, and finally P3 can wait for P4, but it should never wait for P0. That means always the processes, they can wait for another resources. Moreover, in some some ordering should be imposed here, either whether it is increasing order, whether it is decreasing order. So we should never get the circular wait condition. So in this manner, whenever we break any one of these 4 conditions, like either we should violate mutual exclusion, or we should violate hold and wait, or we should violate no preemption, or we should violate circular wait, whenever we break any one of these 4 conditions, so then we can prevent these deadlocks. So this is the first solution, so that we are providing for handling deadlocks. In the next session, so we shall see something about this deadlock avoidance.